Dr. Aik-Hao Ng, who is a senior medical physicist in the Department of Radiotherapy and Oncology, Kuala Lumpur Hospital, and Nuclear Medicine Department at the National Cancer Institute. Dr. Ng obtained his PhD from the University of Nottingham in Radiological and Imaging Science, focusing on the translation of a laboratory prototype handheld gamma camera into clinical use. He is the founder and chairman of the Ministry of Health Medical Physics Research Task Group in Malaysia. He also served as the physics advisory editor for Medical Dosimetry, the official journal of the American Association of Medical Dosimetries. Without further ado, let's welcome Dr. Ng to give his lecture. Dr. Ng, please.
Good morning, good afternoon, everyone. Thanks to ACOMP for providing this training and education platform. My name is Aik-Hao Ng, medical physicist from the Kuala Lumpur Hospital and National Cancer Institute, Malaysia. We are practicing the knowledge of radiobiology in our daily clinical work. Either you are working in the field of radiotherapy, nuclear medicine, or diagnostic radiology. Before we listen to other advanced topics from our distinguished speakers, let us recap on some important terms and concepts in radiobiology. It is my great pleasure to share with you about the radiobiology of tissue interaction with radiation. The objective of this lecture are to understand the characteristic of ionizing radiation, the concept of linear energy transfer, cell cycle and cell death, radiobiological damage of cell by radiation, and the 5 R's of radiotherapy. Since the discovery of X-ray by Wilhelm Röntgen in 1895 and the discovery of radioactivity by Heinrich Becquerel in 1896, these remarkable discoveries had enormous significance to the field of modern physics, either in industry or medicine. It is difficult to envision 21st century's medical practice without the ability to image bone, vessel, and all aspects of human body invasively. The top left corner image shows the first X-ray photograph of Mr. Röntgen's wife's hand. Image in the middle was developed by using radiation that spontaneously emitted in uranium salts that registered on a photographic plan. These were developed in the experiment by Mr. Becquerel. Since then, the technologies have been widely used in medicine, including imaging and therapeutic purposes. After years of application, the scientists had realized about the potential health effects due to the long-term or high dose rate exposure of ionizing radiation. The knowledge of radiobiology and radioprotection has increasingly become more significant. Radiobiology is a branch of sciences which combines the basic principles of physics and biology and is concerned with the action of ionizing radiation on biological tissues and living organisms. It is a study of basic radiobiological mechanisms, deals with biological effects produced by energy absorption in small volumes corresponding to single cells or parts of the cells. Therefore, when we talk about radiation medicine, radiobiology is an important aspect in the diagnostic applications, while it is considered to be essential in the therapeutic applications. These basic principles are used in radiation therapy with the objective to treat cancer with minimal damage to the normal tissues. For example, the dose prescription of radiotherapy treatment for an early stage breast cancer patient is 40 gray in 15 fractions over the 3 weeks. This fractionated treatment enables a few courses of photon irradiation of less than 2 grays to the targets. This treatment regime might have changed in some centers recently to hypofractionation as suggested by the fast-forward trial, which is 26 gray in 5 fractions over a week. In view with current clinical evidence, practicality and cost effectiveness. With the rapidly change in medical practices and technology advancement, the modern treatment poses challenges and opportunities in radiobiology. We can see some examples such as the IMRT, which allows dose heterogeneity and the high dose rate perfractions in SRS and SRT cases. More recently, with the advancement in the precision medicine and the development of the theranostic in nuclear medicine, this has bring the attention of the scientists to discuss further about these issues. Now, let's move to the type of radiation. Electromagnetic spectrum is a range of frequency of electromagnetic radiation and its respective energies and frequencies. You can see from your right radio wave towards to your left gamma rays. With the increasing of frequency, the shorter the wavelength. Radiation is classified into two main groups, non-ionizing radiation, or called as NIR, and ionizing radiation. For NIR, the energy of the radiation is not adequate to ionize the matters, but when it interacts with matters, it can cause excitation. However, for ionizing radiation, the energy of the radiation is adequate to ionize the matter. This is in particular interest when we talk about radiobiology. For ionizing radiation, it can classify into two categories, which is directly and indirectly ionizing radiation. For directly ionizing radiation, which involve charged particles such as electrons, protons, alpha particles, and heavy ions, when it interacts with matters, it can straightaway deposit the dose to the medium. For indirectly ionizing radiation, which involve neutral particles or electromagnetic such as photons and neutrons, it will interact with the charged particles and only will deposit the dose. The figures at the bottom shows the different type of ionizing radiation and its penetrative powers. On the top is the alpha, which is the heaviest charged particles among three with less penetrative powers. It can be stopped by a piece of paper. Beta or electron is relatively lighter than alpha and it can be penetrated better and can be blocked by aluminium. For gamma photon, which is the neutral electromagnetic wave, it has to be blocked by a piece of lead, where the penetrative power is higher among three. As mentioned just now, if radiation is absorbed in biologic material, ionization and excitation occur in a pattern that depends on the type of radiation, whether it is non-ionizing or ionizing radiation. The heavier particles with large charge can produce higher ionization density, and for a given particle type, the energy or the velocity of the particle type is inversely proportional to the density of ionization. In order to define the quality of an ionizing radiation beam, the linear energy transfer is used. International Commission on Radiation Unit and Measurement (ICRU) has defined LED as the quotient dE over dL, where dE is the average energy locally imparted to the medium by a charged particle or specific energy in transversing over distance of dL, and the unit of LED is keV over micrometer. This is different with the stopping power, which focus attention on the energy lost by a charged particle moving through a medium. But LED is focusing on how much of energy absorbed when it travels over the medium. Here are some typical LET values for commonly used radiation. For example, 250 kbp X-ray has an LET values of 2. When we compare with a higher energy X-ray, the 3 MeV X-ray, the LET value is 0.3. This has indicated that when the energy of the X-ray is higher, it has a higher penetrative power, and when it interacts with the medium, it deposits a less dose over a certain distance. And when we compare 3 MeV X-ray with 1 MeV electron, due to the similar energies, the LET value is quite similar as well. For LET values for other or less commonly used radiation, 14 MeV neutron, the LET value is 12. Heavy charged particle, it ranges from 100 to 200. For 1 keV electrons, 12.3, and the higher electrons energy, 10 keV, it is 2.3. Just to reiterate that the LET value depends on the kinetic energy or the velocity of the electron. The LET is inversely related to the electron density. As electron loss energy, its velocity decrease and the value of LET increase until all its energy is dissipated. This table shows the range of the LET values with the increasing electron energies. It ranges from 0.2 up to 12 keV per micrometer. This schematic diagram shows the effect of LET of a particles when it travels across the DNA target. With a lower value of LET, the chances of ionization across the pathway is lesser. If the LET value is increasing, you can see that more events is happening along the medium. And there are more chances of ionization or excitation could be happen at the DNA regions. Therefore, the higher the LET, the higher the probability of direct interactions. This is a classical paradigm of radiation injury, giving us an overview on what will happen over the time period. When the ionizing radiation interacts with metal, it will cause excitation, which will translate as a heat. It may also cause ionization, where more free radicals will be formed, and we will talk more about this in the next few slides. Chemical repair, or the ion can be recombined at this stage as well, and all this will take place in the order of seconds. When ionization occurs, it might damage the DNA. The DNA might undergo repair. However, when this is not successful, cell death or the DNA mutation might happen. For cell death, it can be either early effects or lag effects, or even if the fetus is involved, it might cause the developmental effects to the fetus. For DNA mutation, when it is involved the germline, it might cause the effects to the offspring. And where it involved with the somatic cells, the cancer can be induced. And all this will take place from days to years. All this radiation injury or biological effects take place in a living organism. Now, we talk more about the cell. All living entities are made up of protoplasm, which consists of inorganic and organic compounds that dissolve in water. The smallest unit of protoplasm capable of independent existence. The basic microscopic unit of all living organisms. There are two main constituents of a cell, which are the cytoplasm and the nucleus. The cytoplasm is the liquid surrounding the nucleus, And the nucleus contains the genetic information, which is the DNA, and this is in particular interest when we talk about radiobiology. Outside the protoplasm is surrounded by the membrane. Human cells are either somatic cells or germ cells. Germ cells are either a sperm or an egg. All other human cells are called somatic cells. The cells propagate through division. The division of somatic cells is called mitosis and result in two genetically identical daughter cells. For the germ cells, it is called meiosis and it involves two fission of the nucleus giving rise to four sex cells, each possessing half the number of chromosomes of the original germ cells. Cell proliferation cycle is defined by two times period where mitosis is indicated by the capital letter M, where division takes place. The period of DNA synthesis is indicated by the capital letter S. S and M portions of the cell cycles are separated by two periods called gaps, G1 and G2, when respectively the DNA has not yet been synthesized or has been synthesized but other metabolic processes are taking place. The duration between successive division is called the cell cycle time. Cell cycle time for mammalian cells is of the order of 10 to 20 hours. The S phase is usually in the range of 6 to 8 hours. M phase is less than an hour. G2 is in the range of 2 to 4 hours and G1 is in the range of 1 to 8 hours. Other facts and definition that we need to know of are, for stem cell in certain tissues, the cell cycle times is up to 10 days. The cells are most radiosensitive in the M and G2 phases and most radioresistant in the late S phase. Cell cycle time of malignant cells is shorter than that of some normal tissue cells, but during regeneration after injury, normal cells can proliferate faster. Cell death of non-proliferating cells is defined as the loss of a specific function. Cell death for stem cells and other cells capable of many divisions is defined as the loss of reproductive integrity, or is called as reproductive death. Cell nucleus contains sensitive component for radiation-induced cell killing, not in the cytoplasm. When directly ionizing radiation is absorbed in biological material, damage to the cell may occur in one of two mechanisms. It can be either direct or indirect actions. For direct action in cell damage by radiation, most of the particulate radiation interacts directly with the critical targets in the cell. The atoms of the target itself may be ionized or excited through column interactions, leading to the change of physical and chemical events that eventually produce the biological damage. Dominantly process interaction of high LET particles such as neutrons or alpha particles with biological material. For indirect action caused by X-ray or gamma ray photons, the photon interact with an atom in the cell, produce a charged particle such as electron or positron, which subsequently interacts with the DNA. The radiation interacts with other molecules and atoms. 80% of the mass of a living cell is water, so the free radical will produce within the cell. A complex series of chemical changes occurs in water, which is called water radiolysis. Through diffusion in the cell, free radicals damage the critical target within the cell. This indirect action can be modified by chemical sensitizers such as hypoxic sensitizer or radiation protector. When interaction of radiation with water, Basic radiochemical reaction that may occur in water molecules causes ionization and excitation process, producing ion radical and subsequently water radicals such as hydroxy radical, hydrogen atom, and hydrated electron. These radicals are highly reactivity towards molecules of cells, which will bring about indirect radiation damage to biological system by reacting and damaging in the molecules in cells. The reason why the free radicals are highly reactive molecules because they have an unpaired valence electron. About 2/3 of the biological damage by low LET radiation, spatially ionizing radiation such as X-ray and electron, is due to indirect actions, and 1/3 is due to direct actions. Steps that involve in producing biological damage by the indirect action of X-ray are as follows. Primary photon interacts produce a high energy electrons or positron, and this is a physics process. High energy light charged particle in moving through tissue produce free radicals in water. This is a chemistry process. And then the free radical may produce chemical change in DNA from the breakage of chemical bond. Subsequently, changes in chemical bonds result in biological effects. This timescale shows the effects of radiation exposure on biological systems. The physics of the process takes of the order of 10 power of minus 15 seconds. The ion radical have a lifetime of the order of 10 power of minus 10 seconds, and the free radicals have a lifetime of the order of 10 power of minus 5 seconds. The steps between the breakage of bond and the biological effects may take hours, days, or years. Now, let's move to the 5 R's in radiotherapy. Radiation therapy has traditionally been a fractionated treatment course spread over several weeks. Take advantage of differential repair abilities of normal and malignant tissues. Typically produce better tumor control for a given level of normal tissue toxicity than a single large dose. The most important biological factors influencing the response of tumors and normal tissues to fractionated treatments are often called the 5 R's: repair, repopulation, redistribution, reoxygenation, and radiosensitivity. Repair of sublethal damage to cells between fractions caused by radiation. For single-strain break, little biologic consequences because they are repaired readily using the opposite strain as a template. For double-strain breaks, not usually repairable if the breaks are close together, may result in cell killing, carcinogenesis, or mutation. For the repopulation, both normal and cancer tissue proliferate during the course of therapy. This has resulted to the regrowth of cells between the fractions. Hence, it increased the number of cells during the course of the treatment and reduced the overall response to irradiation. This is important in early responding normal tissue such as skin, GI tract, or in tumor whose stem cells are capable of rapid proliferation. Little consequences in late responding, slowly proliferating tissue such as kidney. For redistribution, it is relates to the cell cycle effect. Variation in the radiosensitivity of cells in different phases of the cell cycle results in the cells in the more resistant phases being more likely to survive a dose of radiation. Two effects can make the cell's population more sensitive to a subsequent dose of radiation. Some of the cells will be blocked in the G2 phases of the cycle, which is usually a sensitive phase. Second, some of the surviving cells will redistribute into more sensitive part of the cell cycles. For reoxygenation, it is related to the oxygen effect. Oxygen is a powerful radiation sensitizer. So, tumors that are poorly oxygenated, such as hypoxic tumor, tends to be resistant. Hypoxic tumor can reoxygenate during a course of treatment, separated in time sufficient for reoxygenation to occur and become more radiosensitive. For radiosensitivity, it is to explain at the mechanistic level the different radioresponsiveness of the disease. It is worth noting that for different individuals, the radiosensitivity among the normal cells and the tumor cells will be different. Cells from different type of tumor differ markedly in their inherent radiosensitivity. This table shows the sensitivity of different tumors. For example, for highly sensitive, such as germ cell tumor, multiple myeloma, up to the lower resistance such as sarcoma, adenocarcinoma. Based on the current research development and publication, it is suggested that the 6 hours should be added. However, it varies between remote bystander effects or reactivation of anti-tumor immune response. Bystander effect is the phenomenon in which unirradiated cells exhibit irradiated effects as a result of signals received from nearby irradiated cells. For reactivation, it is believed that radiotherapy is able to modify the tumor environment and to induce systemic and immune-mediated anti-tumor response. Some bring home messages. Linear energy transfer is the average energy locally imparted to the medium by a charged particle of specific energy traveled through a distance. This is in the unit of keV over micrometer. Cells are most radiosensitive in the M and G2 phases and most radioresistant in the late S phase. For direct action, the radiation interacts directly with the cell's nucleus. For indirect actions, the radiation interacts with water molecules, produce free radicals such as hydrated electron, hydroxy radical, and hydrogen atom, and then damage cell nucleus. The timescale of the effect for physics, free radicals, and biologicals are different as here. For 5 hours, it involves repair, repopulation, redistribution along cell cycle, reoxygenations, and radiosensitivity. And most recently involved the 6 hour, which is varies from remove bystander effects or reactivation of anti-tumor immune response. These are the references, and thank you for your attention. Thank you, everyone.